Good morning everyone, and welcome to today's worked exam answer video. Today I'm having a look at a structure and bonding question, a GCSE structure and bonding question, and this particular question has come from an Edexcel iGCSE double award paper, but the contents of the question and what we need to understand also apply to those of you studying AQA as well. So we're having a look here at three different structures of carbon. And that, I guess, is the first really important thing for us to notice or to recognise in the question, because all of these structures, structure A, graphite and C60 fullerene, are only made up of carbon. Now, these different structures behave differently. There's some similarities between some of them, but there's also quite major differences between some of them, and that's based on how those carbon atoms are bonded together, and that's what the question is essentially getting at further down. So we have got different structures of carbon, and the first thing we need to be able to recognise is what structure A is. So that's hopefully a diagram that you're a little bit familiar with. That represents the structure of diamond. So that is the answer for the first part of our question here. And we do need to know that diamond is one of the forms of carbon that they're likely to ask about. Another form of carbon that they're likely to ask about is graphite. Then we've got these fullerenes, and if you're studying the AQA specification, they might also ask you about graphene, which is a single layer of your graphite, and you've also got things like carbon nanotubes as well. So we can recognise structure A as diamond because in diamond we need to know that every carbon atom is bonded to 4 other carbon atoms, and then we're going to get this kind of ever expanding structure if every carbon is then bonded to 4 others. Graphite, a bit different from diamond in that each carbon is only bonded to 3 others, and that's why we get these layers, because we don't have the 4th bond that would be connecting these layers together. And that's the major difference between diamond and graphite. That isn't what this question is asking of us. This question is then asking of us to compare graphite and C60 fullerene. Now again, the key thing is here, they've told us that they contain covalent bonds. Both of them contain covalent bonds, which if they're types of carbon or forms of carbon, makes sense because carbon atoms are non-metal atoms, and we get covalent bonds when non-metal atoms share their electrons, but it tells us that they have got different structures. And when we're thinking about structures, we're thinking about how those covalent bonds between those atoms, I guess, overall are arranged. So we can see in C60 fullerene that they're kind of arranged into like football shapes. We've got these like hexagons, like the really old footballs from back in the day, before my day even, but there's only 60 carbon atoms in that one fullerene molecule, and then you'll have another C60 fullerene made up of another 60 carbon atoms, and you'd have that on repeat. With graphite has a very different structure because you have sort of no upper limit to the amount of atoms. So in C60 fullerene there are 60 carbon atoms. In graphite there will be hundreds of thousands of millions potentially of atoms of graphite in these layers, and that gives us the different properties that they go on to ask about. So it says explain why C60 fullerene has a much lower melting point than graphite, and we have to refer to structure and bonding in our answer. And when it says that, obviously we need to be making sure that we are making reference to both the structure and the bonding, which again might sound like a really basic thing to say, but some students will kind of omit to do that because they'll get so into sort of answering the question and going straight into the specifics of why, that they will miss out some easy marks by not quite answering that part. So the key thing that we're trying to explain is why C60 fullerene has a much lower melting point than graphite. And I guess the first thing that we should really think about is, what are these different structures? I know I've kind of referred to them as being, you know, a football kind of shape where we have a maximum of 60 carbon atoms in there, and that graphite, you've got hundreds of thousands and possibly millions of carbon atoms in there. But we can give names to those type of structures. Now, when we have covalent bonding, there is a possibility that we will have two different structure types. We might have giant covalent structures, which is what both diamond and graphite have. Or we might have simple molecular structures. So we might have molecules. Now, you may have been taught the word macromolecular instead of giant covalent, macro meaning big, molecular molecules. Not really a fan of that word myself. I will always go with giant covalent for these type of structures, and then simple molecular for these. And those are the structure types, and it is what we are wanting to do to these structures in order to melt graphite or melt C60 fullerene that explains why the C60 fullerene has a much lower melting point than graphite. So that's where the bonding bit then comes in, because when we are trying to melt graphite, we need to break all of the covalent bonds between all of the carbon atoms. And the word giant here isn't sort of referring to overall size, it's referring to the number of carbon atoms and the number of covalent bonds between all of those carbon atoms, and all of those bonds would need to be broken. So that's what the word giant is referring to. And if we're having to break a lot of very strong covalent bonds, we're going to need a lot of energy to do that. So the melting point of graphite and the melting point of diamond are both very, very high. C60 fullerene, on the other hand, and all simple molecular structures, when it comes to melting them, we're not actually going to be breaking those covalent bonds within that singular molecule. The football is going to stay in its football shape, and all of those bonds will remain intact. When it comes to simple molecular structures, we're not breaking the strong covalent bonds, we're overcoming weak intermolecular forces that exist between the C60 fullerene molecules. So if I had another C60 fullerene molecule here, they would be held in fairly close proximity by some weak intermolecular forces. And the word intermolecular means between molecules. And what we want to do if we've got two C60 fullerene molecules is we want to move the whole molecule away from another molecule. So we're not changing what's in either of those molecules, we're just moving the molecules further apart. Those intermolecular forces are very weak, and they take little energy to overcome, far less energy to overcome than the strong covalent bonds. So the covalent bonds in the C60 fullerene itself are still very strong bonds. The difference is we're not breaking those here. We are overcoming the weak intermolecular forces. So now I need to try put that together in my answer. Now, we don't need to worry about writing in sort of continuous prose. I'm not going to do that here. It's not the way I like to work. I'm going to kind of go for a more kind of bullet pointed, concise answer, which is absolutely fine to do for this. So the first thing that I'm going to do for each substance is I'm going to say what bonding there is. I mean, we're told that they both have covalent bonds, but I'm going to state that anyway. So we've got covalent bonding and a giant covalent structure, and then in C60 fullerene there is still covalent bonding, but now we have a simple molecular structure. And now I need to talk about the fact that we are breaking bonds to melt graphite, whereas we're overcoming weak intermolecular forces to melt the C60 fullerene, and that breaking the covalent bonds takes a lot more energy than it does to overcome these intermolecular forces. The wording used in the question is comparative, so it has a much lower melting point, so we need to make sure that we're making a comparison, and we can do that by saying it'll take lots of energy to break the covalent bonds in the graphite, and it'll take little energy to overcome the weak intermolecular forces, as sort of separate sentences, or we can kind of wrap it up all in one comparative sentence. But it is really important that we are using a comparison here based on the language in the question. So I'm going to say that lots more energy is needed to break all of the very strong covalent bonds in graphite than is needed to overcome the weak intermolecular forces of attraction between the C60 fullerene molecules. And again, it might then be good to refer back to how that connects to the melting points. If more energy is needed to break bonds, then it's going to have a higher melting point. We're going to need to put more energy in to melt it, higher temperature overall therefore required. Not going to get us a mark here because they've already sort of related the melting point of fullerene to graphite, but if you wanted to wrap it up with that, you could, and it's always good to, I guess, consider going back to the question and making sure we've actually answered kind of what the question is asking of us. So I'll round off with, therefore, the melting point of graphite is much higher than the melting point of C60 fullerene. Please don't write in that part of the paper in your actual exam, because those are the bits that won't get scanned in necessarily, so just write it underneath an MP for melting point, because I knew I was running out of room. But that is how we answer a comparative question like that. I've referred to the structure and the bonding because I've straight up stated the bonding and structure of both of them, but then I've also talked about the bonds that are being broken in graphite and then the forces between the molecules that are being overcome when we're melting the C60 fullerene, which is referring to the structure because all simple molecular structures have these weak intermolecular forces. So hopefully that's been useful. I know that it can be tricky to answer questions like this for structure and bonding. So if you've got any other similar questions or slightly different questions that you want me to have a look at, as always, please let me know. Leave me a comment on the video, or you can send me an email to missgtutoringandresources@outlook.com. Thanks so much for watching, guys. Hope you have a wonderful day.